Lighthouse Scientific Education presents a lecture in the Nuclear Chemistry series. The topic, Nuclear Chemistry, Part 1. Material in this lecture relies on an understanding of the previous lecture, Basics of the Atom. Our study of nuclear chemistry begins with a review of the atom and of isotopes. Some new terminology is included in this section. This leads to a graph that shows the stability of a nucleus based on its proton and neutron ratio. Unstable nuclei are considered radioactive. A brief history of the early work done in nuclear chemistry is given. Ionizing and non-ionizing radiation are covered, followed by the important topic of radioactive decay. 3 types of decay are explored: alpha, beta, and gamma. The last topic is writing and balancing nuclear equations. Up to this point in our studies, the focus has been on what the electrons are doing. In this series, the focus shifts to the nucleus. A review of the atom. Atoms are comprised of 3 different subatomic particles: protons, neutrons, and electrons. 2 of those subatomic particles, the proton and the neutron, are called nucleons. As the name suggests, nucleons are found in the nucleus. The 3 particles differ in their mass and charge. The subatomic particles are given a symbol indicating mass and charge. The proton has a mass of 1 AMU. The AMU is a unit based on the mass of the proton, which is 1.660 times 10 to the minus 27th kilograms. The 1 in the upper left-hand corner indicates the mass in AMU of a particle. A proton has a charge of +1. No plus sign is needed. Charge is indicated in the lower left-hand corner of the symbol, often a P with a superscript plus, for +1 is used to indicate a proton. The neutron also has a mass of 1 AMU, but it has no charge, as indicated by the 0 in the lower left-hand corner. Its shorthand is just a lowercase n. The electron weighs about 1/2000th as much as a proton or a neutron. Its mass is usually neglected, as noted by the 0 in the upper left-hand corner. It does, however, have a charge. The charge is -1. The electron is often denoted as an E with a superscript negative sign. An element is a pure substance that is made up of only one or a single type of atom. The periodic table holds the elements in place. It is the number of protons in the element. A closer look at the construction of the element symbol in the table brings up important terminology that we will be using when we deal with nuclear equations. We know each element gets its own symbol. Along with the symbol, there are generally 2 numbers. The smaller of the 2 is the atomic number. It is the number of protons in the element. For an atom, it is also the number of electrons. And then there is the mass number. It is the number of protons plus the number of neutrons. The total number of nucleons. Using helium as an example, it has an element symbol of He, an atomic number of 2, and a mass number close to 4. Remember, mass numbers in the periodic table are based on averages of a large number of atoms of that element. Individual atoms will have whole numbers for their mass numbers, since it is a count of the number of protons and neutrons in that atom's nucleus. So, according to the atomic number for helium, it has 2 protons. To get a mass number of 4, this atom must have 2 neutrons. This level of understanding of the mass number is required in dealing with balancing nuclear equations. While we have this construction for helium up, there's one area where regular chemistry and nuclear chemistry differ in how they present atomic number and mass number. In regular chemistry, the atomic number is on the top and the mass number is on the bottom. When dealing with the symbol in nuclear chemistry, the mass number is on top and the atomic number is on the bottom. One more point. Nuclear chemistry is concerned with what's going on in the nucleus, and the atomic number is not what is actually used with the symbol. That is given over to the nuclear charge. There's a great similarity with atomic number and nuclear charge when they are both counting the number of protons. But with nuclear charge, there's an overlap with the structure of the symbol for subatomic particles. Helium has a +2 charge in the nucleus, and the electron has a -1 charge. Written this way, the symbols are speaking the same language. The other review topic is isotopes. Isotopes are the same atom type with different number of neutrons. They have the same atomic number, same number of protons, but they differ in mass number. The only way for that to happen is if there are different number of neutrons. In the Basics of Atom lecture, we looked at isotopes of hydrogen as an example. By far the most abundant isotope of hydrogen is the one called ordinary hydrogen. It has 1 proton and no neutrons. Its mass number is 1. The sum of the number of protons and neutrons is 1. The nuclear charge is +1 for the 1 proton in the nucleus. And then there is deuterium. It is also an isotope of hydrogen, so it must have 1 proton. Deuterium, though, has a neutron. It has a mass number of 2. It still has a nuclear charge of 1. There's also an unstable isotope of hydrogen called tritium. It too has 1 proton, but this nucleus has 2 neutrons. It has a mass number of 3. How do we know which isotope of hydrogen is which? Look at the mass number. The nuclear charge is unchanged, but not the mass. That leads us to the band of stability. It is a recognition that not all nuclei are stable. Some combinations of protons and neutrons in a nucleus destabilize or weaken the integrity of the nucleus. The stability of a nucleus is not a thing that can be determined from principles. These things have to be measured in a lab. When such measurements are gathered together and plotted on a graph, they show a band of stability or a region of stable nuclei as a function of atomic number and the number of neutrons. The plot has the number of protons in a nuclei on the x-axis and the number of neutrons in that nucleus on the y-axis. Small atoms like helium will fall to the far left, and large atoms like lead will be on the far right of this graph. A dotted line shows nuclei that have the same number of protons as neutrons. The blue curve with a light pink highlight indicates the more stable nuclei. Not all combinations of protons and neutrons are stable. Stability of a nuclei for atoms with a low atomic number, like helium, occurs when the number of protons is approximately equal to the number of neutrons. That's here on the curve. The dotted line and the blue line overlap. The stability of nuclei for atoms with a higher atomic number, like lead and mercury, occurs when the number of neutrons is more than the number of protons. That's up here on the graph. The rule of thumb is that as the atomic number goes up, the band of stability becomes steeper. Neutrons are added faster than protons. For helium, stability of its nuclei occurs when the number of protons equals the number of neutrons. For mercury, stability of its nucleus occurs when the number of neutrons far exceeds the number of protons, 80 protons to 120 neutrons. So why is there differences in stability? A closer look at the nucleus has its stability based on two great forces. The first is charge-charge repulsion. Protons are positively charged. One proton repels another. They do not want to be next to each other. If the nucleus was only protons, it would never form. The second force is the strong nuclear force. It is an attractive force between all nucleons, be they protons or neutrons. We will not get into the details of the strong nuclear force. Rather, we will take a simplistic view and say that it behaves like a glue. The two great forces are acting in opposite directions. The first seeks to destroy the nucleus, and the second to hold it together. As for the steepness of the band of stability, seen with larger nuclei, the more protons the nucleus has, the larger the atomic number and the larger the nuclear charge it has. That requires there to be more strong nuclear force to keep the protons from separating, that is, splitting the nucleus apart. Is the strong nuclear force that the protons themselves have strong enough to do this? No, it is not. Neutrons provide additional strong nuclear force, and they are needed in more than a 1-to-1 ratio with larger nuclei. Big nuclei need more glue. What separates ordinary chemistry from nuclear chemistry, among other things, is the magnitude of energy involved. Separating nucleons releases energy. All that pent-up proton-proton repulsion is released. The energy that accompanies the nuclear reaction will stem from how these two great forces play out. But not all nuclei participate in nuclear chemistry. That is left to nuclei that do not fall in the band of stability. Those nuclei are said to be radioactive, also known as radioactivity, radioisotopes, or radioactive decay. Decay is the common term, and it means loss or diminishing. Radioactivity is when particles or energy are emitted from the nucleus of an unstable atom or isotope. Unstable atoms or isotopes are said to be radioactive. Because radioactivity releases energy, it can damage living cells. Radioactive materials are potentially dangerous, and precaution must be taken. What really distinguishes decay is that a small amount of mass is converted into a very large amount of energy. That follows from Einstein's famous equation, E equals mc squared. A very small amount of mass, m, multiplied by a very large number, speed of light squared, is a large amount of energy, E. But the change in mass is really very small. It's much less than the mass of a tiny electron. In fact, it is so small that it doesn't come into play when dealing with the mass of atoms or protons or neutrons. Essentially, it is ignored when mass is considered. While we acknowledge that there is a conversion of mass, we also acknowledge that it is so small that we need not include it in our mass calculations. Yes, a bit of a contradiction there. While a very interesting topic, the tiny mass is not one explored at this level of chemistry. Radioactive decay is a spontaneous process. Spontaneous does not mean fast, it means eventually, though that can be fast. At the isotope level, there is uncertainty. That is, which unstable atom or isotope in a sample will undergo decay at any particular time is unknowable. It's like knowing which kernel will pop when making a bag of popcorn. Individually, the kernels pop at random times, but the overall pattern of popping is knowable. Unstable atoms or isotopes appear to randomly decay. The decay follows a statistical probability over time. Here's a typical decay curve. Time is on the x-axis. It starts at time 0. With the sample, there's only one type of unstable atom or isotope. At time 0, there is 100% of that isotope. It's like that bag of popcorn. At time zero, 100% of the kernels are unpopped. As time goes by, more and more of the sample undergoes decay. The percent of isotope that is not decayed, that still remains, decreases. It does so in an exponential manner. Given long enough, almost all of the material will have decayed. Close to zero would remain. Same with the popcorn. Given long enough, almost all the kernels would pop. But for an isotope, how long is long enough? For that discussion, see the topic half-life in the next lecture. As a form of chemistry, radioactivity is not that old. It was first discovered in 1896 by Henri Becquerel. He called the emissions he found uranic rays, since they came from uranium. Becquerel showed that uranium could expose film in the absence of light. His emissions would come to be called radiation. Marie and Pierre Curie were the first scientists to isolate radioactive materials. They showed emissions come from unstable atoms. These were termed radioactive atoms. The Curies would go on to identify two new elements, polonium and radium, and would receive the Nobel Prize. Unfortunately, they did not know how dangerous the radioactive material was. Marie and her daughter would die of cancer due to their exposure. Radiation in its broadest sense is characterized as ionizing and non-ionizing. The distinction is no less important than dangerous and not dangerous. Non-ionizing radiation does not knock an electron off an atom. It does not form ions, hence its name, non-ionizing. An example would be microwaves. Most forms of non-ionizing radiation have been shown to not be dangerous. Some forms still require further study to set their danger level. That is, there is currently no conclusive proof that they are dangerous, but there's some circumstantial evidence that warrants further study. Cell phones fall in that category. Ionizing radiation, however, can knock an electron off an atom. That will form ions, which can lead to the formation of free radicals. X-rays are an example of ionizing radiation. This form of radiation is dangerous to life forms. Unwanted ions or free radicals can damage DNA, and that could be life-threatening. Human exposure to radiation is measured in a unit called the rem or millirem. People who work near radiation have to monitor the amount of radiation that they're exposed to. Where does radiation come from? Broadly speaking, there are two major sources. There is man-made radiation. This is limited to the past 120 years. Some medical devices use radiation, the most popular being X-rays. There is also nuclear power or energy. Nuclear bombs fit into this category too. With the exception of medical procedures, most people get the majority of their exposure, most of their millirems, from background radiation, including cosmic rays. These are high-energy particles that come from outside our solar system. On average, we are struck by a couple hundred cosmic rays per second, but most do no harm. And depending on where you live, radon exposure can be a big deal. Radon is a decay product from the uranium that is found in granite bedrock. There are also naturally occurring isotopes, like carbon-14. For some students, it's a little shocking to see the variety and amount of radiation that we're exposed to. Fortunately, on this planet, life has evolved to handle a certain amount of radiation. Still, it's probably a good idea to be able to identify the sources. That is where detection comes in. There are many different types of radiation detectors. The earliest form, and still an effective means, is photographic film. X-rays are passed through tissue, and unless they strike a hard surface like bone, will pass straight on through and expose the film. People who work around radiation are required to wear a dosimeter. Usually it's a badge with film in it. As the person is exposed to radiation, the film also gets exposed, which develops some of the film. The amount of developed film is a proportional gauge to the cumulative exposure of the wearer. As mentioned earlier, radiation absorbed by people is measured in a unit called rem or milliram. The average person gets about 650 millirems of exposure each year. For the big stuff, there's the Geiger counter. It has a probe that measures ionizing radiation and converts that measurement to sound. We're familiar with the tick, tick, tick that comes with pointing the device at a radiation source. The next topic is an important one. We will look at 3 major types of radioactive decay and then employ them in balancing nuclear equations. Each type is a particle emitted from the nucleus. Particle is used loosely here. It will also include energy emitted from the nucleus. The 3 are alpha decay, beta decay, and gamma ray emission. All 3 are forms of ionizing radiation. That is, they have enough energy to pull or knock an electron or electrons away from matter. This is why radiation is dangerous to living cells. Let's look at all 3 in more detail, starting with alpha decay. It is the loss of an alpha particle from a parent nuclei. An alpha particle is really just a helium nucleus. It consists of 2 protons and 2 neutrons. It does not have any electrons. An alpha particle has a mass number of 4, 2 protons plus 2 neutrons, and a charge of +2 from the protons. We can look at the decay of the unstable isotope of uranium-238. It has 92 protons, as denoted by the charge of 92. At some random point, the nucleus of a U-238 atom will eject an alpha particle, helium nucleus, leaving an isotope with a slightly smaller nucleus. Slightly smaller since it has 2 less protons and 2 less neutrons. The element that has 90 protons is thorium. Uranium has changed into thorium through alpha decay. Later in the lecture, we will talk about why this is a balanced nuclear equation. For now, there's a couple terms that should be covered, such as parent nuclei. This is the isotope prior to decay. The atom or isotopes or ions that come out of decay are called the daughter nuclei. Both the thorium and helium are daughter nuclei in this reaction. The parent-daughter naming does make a certain sense because one comes from the other. The next type of decay is beta. It is the loss of a high-energy electron from a parent nuclei. Beta is the Greek equivalent of the letter B and has the nuclear designation of E for electron, with a mass number of 0 or approximately 0 and a charge of -1. It is an electron. How does the nucleus lose an electron? Aren't electrons outside of the nucleus? Yes, they are, but those electrons are not part of beta decay. It turns out that our current understanding of the neutron is incomplete. A neutron can split into a proton and an electron. That is definitely a new way of looking at the neutron. It probably needs a bit more of an explanation. Returning to the symbol of the 3 subatomic particles that make up the atom, the mass number is in the upper left-hand corner and the charge in the lower left-hand corner. Starting with a neutron and its mass of 1 AMU and its charge of 0. Under the right conditions, it can split into a proton and an electron. The details are beyond our current understanding of chemistry, but we could do some housekeeping to show that the process does follow our current understanding. That has us making sure that the mass and the charge are the same on both sides of this equation. In essence, this is our first balanced nuclear equation. Starting with mass. On the neutron side, the total mass is 1 AMU, as is the total mass on the proton and electron side. The neutron can split without an appreciable change in mass. Charge is a bit trickier. The neutron has no charge, but the proton and the electron do. Keep in mind that we are tracking the total charge, so the +1 of the proton is added to the -1 of the electron. That sums to 0. The splitting of the neutron is consistent with mass and charge. Where might we come across beta decay? Carbon-14 is a good place. Carbon-14 is covered in more detail in the half-life section of the next lecture. Here it is used to show that ejecting an electron from the nucleus of carbon forms a nitrogen atom. One of the neutrons in carbon becomes a proton in nitrogen. The nuclear charge went from 6 to 7. There is still that -1 charge on the electron to keep the overall charge balanced. The parent-daughter naming structure still holds, even though the daughter has a higher atomic number than the parent. The third form of decay that we will cover is gamma rays. It is the emission or ejection of a gamma ray from a parent nuclei. Gamma is a lowercase Greek letter. It's like our G. A gamma ray is electromagnetic radiation. It is light. It is a high-energy photon. Essentially, a gamma ray has no mass or charge. No mass, no charge. Gamma ray emissions often follow alpha or beta decay. It is the relaxation of an excited state in the atomic nuclei. An asterisk is often used to indicate that a nucleus is in an excited state, that is, it has extra energy. An example of just gamma ray decay is the excited nucleus of technetium, atomic number 43. It can emit a photon of light. Since the light has no mass or charge, there will be no change in the mass or charge of the daughter nuclei. It will still be technetium. There is an asterisk to indicate that the parent nuclei is excited, but not one on the daughter. That extra excited energy is given off in the form of light, gamma rays. The three types of decay can be compared in 3 ways. First is in their penetrating capacity. The second is in their ionizing ability. And the third one is the ability to be deflected in an electric field. First are the comparison made by penetrating power. A particle ejected from a nucleus is going pretty fast. Penetration means how deep the ejected particle can go in some particular material. It can also be thought of as what material a decay particle can pass through. Penetrating power is based on the energy and the size of the particle. Importantly, protection from radiation is also based on penetrating power. Stop the penetration and stop the radiation. All right, consider a piece of paper, a plank of wood, and a block of concrete. The paper is obviously the easiest thing to penetrate, and the concrete is the hardest. The alpha particle is the largest and heaviest of the 3 types of decay. Being larger, it has trouble passing through solid matter. Paper can stop it, so can skin. The beta particle, being an electron, is smaller. It can pass through the paper and into the wood. The gamma particle has no mass. It is light. It takes the block of concrete to stop it. The gamma ray is by far the better penetrator. The second important feature of the decay particles is their ability to form ions or free radicals. For the alpha decay, one alpha particle can ionize 10,000 atoms. It has a low capacity to penetrate, but a very high capacity to ionize. For beta decay, one beta particle can ionize 100 atoms. It has a medium capacity to penetrate and a medium capacity to ionize. The gamma ray has a much weaker capacity to form ions. It's about 1 gamma ray to 1 atom. So even though it has a very high capacity to penetrate matter, it can't do very much. Given these values, we can see that the radiation suit is designed to stop the penetration of the alpha particle and some of the beta particles. It is the ionization by the alpha particles that is the real danger. The third way to characterize the 3 decay particles is based on charge. Say we have a radiation source capable of emitting all 3 particles, alpha, beta, and gamma. It would be nice to monitor the emission, so we put a detector a certain distance away, oriented to catch the particles. Turn on the source and shoot the particles right into the detector. Now, to make it interesting, say an electric field is applied across the path of the emitted particles. The electric field is oriented with a positive charge electrode above the path of the particles and the negatively charged electrode below the path. We should expect the electric field to have an effect on particles with a charge. Remember, gamma rays have no charge. But beta particles have a -1 charge, and alpha particles a +2 charge. So, if a particle passes through the electric field unchanged, it must have no charge. That must be the gamma ray. What if the path of a particle starts to bend up as it passes through the electric field? That would mean it was attracted to the positively charged electrode. Which particle is attracted to a positive charge? The beta particle. It's an electron with a negative charge. Opposite charges attract. A different particle has its path bent towards the negative charged electrode. Which particle is attracted to a negative charge? The alpha particle with its +2 charge. This kind of deflection was actually used in the early days of atomic theory to figure out what the atom was really made of. Okay, putting it all together in a table. The alpha particle is a helium nucleus. It has a mass of 4 AMU and a charge of +2. It has a hard time penetrating paper, but it can do serious harm through ionization. The beta particle is a high-energy electron. It is treated as having no mass and a charge of -1. It is a better penetrator than the alpha particle and not as dangerous. The gamma ray is light. It is a high-energy photon. It has no mass or charge, and while it is a deep penetrator, it is a poor ionizer. These 3 are the most commonly studied particles in nuclear chemistry. But there are others. We'll quickly look at a few. There is electron capture. An electron combines with a proton in the nucleus. There's no emission here, but rather the formation of a neutron from a proton. It is really just the opposite of the beta particle emission from a neutron we saw earlier. Electron capture happens when an electron gets too close to the nucleus, and a proton and electron combine to form a neutron. And then there is the positron. It is an antiparticle. It is antimatter. Its decay is the loss of a particle that has the same mass as an electron, but has an opposite charge. Its symbol would still be an E with a mass of 0, but the charge is a 1, a +1. The electron symbol has the familiar -1 charge. When these two meet, they annihilate each other and produce energy. That energy can be put to good use. A PET scan, or positron emission tomography, is an imaging technique that is used to observe metabolic processes in the body. An example of positron emission has carbon-11 producing boron-11 by kicking out a positron particle. There are more particles in nuclear chemistry, but this is a good list. The last topic in the lecture is the nuclear equation. In balancing a nuclear equation, we must make sure that the mass is conserved. That is, the sum of the mass numbers before the reaction must equal the sum of the mass numbers after the reaction. We will be using mass number in the symbol. Charge will also need to be conserved. The sum of the nuclear charge before the reaction must equal the sum of the nuclear charge after the reaction. This also includes the charge of any particle ejected from the nucleus. We will be using the charge in the symbol for that math. 4 example problems are offered to practice this process. The first 2 will be demonstrations, and the second 2 will use the rules to find unknown components. Keeping our rules, the first equation is the alpha decay of uranium. Is this equation balanced? Is mass balanced? We can check that by using the equation with just the mass numbers. Uranium-238 has a mass number of 238. On the daughter side is the mass number of thorium-234, and the mass number of 4 from the helium nuclei, the alpha particle. 234 plus 4 equals 238. Yes, the two sides have the same mass. What about charge? Same process. Start an equation that looks at the nuclear charge of the two sides of the nuclear reaction. Uranium has 92 protons and a charge of plus 92. Thorium has 90 protons and a 90 nuclear charge. The alpha particle brings a plus 2 charge from its 2 protons. 90 plus 2 is 92. We see that both sides have a charge of 92. This is a balanced nuclear reaction. Example 2 is the beta decay of carbon-14. Checking to see if it is balanced begins with verifying the conservation of mass. Is the sum of the mass numbers the same on both sides of the equation? The parent radioactive isotope has a mass of 14 AMU. The decay products have a mass of 14 AMU from the nitrogen and essentially no mass from the electron. Yes, mass is conserved. And charge? Carbon has 6 protons and a plus 6 nuclear charge. Nitrogen has 7 protons and a plus 7 nuclear charge. The only way for the two sides to have the same charge is by adding a -1 charge from the electron. 7 minus 1 is 6. The number of protons is not equal, but the total charge in the nucleus, or what was ejected from the nucleus, is equal. The third example is the alpha decay of astatine into bismuth. We will play around with this equation as a way to demonstrate the types of questions that can be asked concerning balanced nuclear equations. First, we will verify that it is balanced. Mass is balanced. Both sides have a mass of 217. Charge is balanced. Both sides have a total of 85 protons and a nuclear charge of 85. Okay, let's keep this equation, but act as if we were not given the bismuth. It is an unknown, and we are asked to determine its identity. Really, this is just the repeat of the same steps that we did in verifying the original equation was balanced. There's a bit more math involved, but it's not complicated. Since the requirement is that mass be conserved, a look at the masses that we have should give us a clue into the mass that we do not have. The acetine has a mass of 217 AMU, and the alpha particle decay has a mass of 4 AMU. What value in AMU must be added to 4 to get 217? Algebraically, this solves as the unknown is equal to 217 minus 4. It's 213. The unknown mass is 213 AMU. Is this enough information to identify the unknown? No, it isn't. Any number of different isotopes can sum to that mass. We need to look at charge. The charge will give the number of protons, and that is enough information to get the element. The acetine has a charge of 85. It has 85 protons, and the helium nucleus has 2 protons. What value in charge must be added to 2 to get to 85? Mathematically, this solves as 85 minus 2 equals 83. Our unknown has 83 protons. To identify the unknown, we take the number of protons to the periodic table. 83 protons is an atomic number of 83, and that is bismuth, just like it was supposed to be. With a calculated mass number and nuclear charge, the equation can be properly completed. Staying with this equation, a similar question focuses on the type of decay. Given the mass number and the charge of acetine and bismuth, what type of decay has occurred? What can we get from the conservation of mass? The mass of 217 and 213 are gotten from the atomic symbols. The question becomes what must be added to 213 to get to 217. Not the most challenging of equations. It is 4. The mass part is complete. As for charge, we have the number of protons from acetine and bismuth is 85 and 83 respectively. That is the nuclear charge. What must be added to 83 to get to 85? That, of course, is 2. Our unknown has 2 protons. That is exactly the information needed for a consultation with the periodic table and an identification of helium. The unknown is helium, and our decay is an alpha particle. In this last example, the daughter atom is not given. We see that iodine 131 has undergone beta decay. It has thrown an electron from its nucleus. To identify the unknown, start by balancing the mass. The iodine has a mass number of 131. The beta particle is an electron and essentially has no mass. That means the unknown must also have a mass of 131. It is with the charge that we will be able to identify the unknown. The iodine has 53 protons for a positive 53 charge. An electron has a charge of -1. What, when added to -1, gives a positive 53? This time the math is a little bit trickier. The algebra comes to 53 plus 1 for a charge of 54. The unknown has a charge of 54. It has 54 protons, and an atomic number of 54 is the element xenon. Our unknown is xenon with a mass number of 131. Balance the mass, balance the charge, and complete the equation. Let's wrap this up by comparing and contrasting the chemical reaction and the nuclear reaction. Chemical reactions only involve changes in valence electrons. In nuclear reactions, there is no change in valence electrons. Chemical reactions have no change in the nuclei. Nuclear reactions do. Chemical reactions have no change in mass in reactant and product. Nuclear reactions do have a small change in mass. It is so small that it is ignored when dealing with mass in a nuclear equation. Still, that small mass change produces a lot of energy. E equals mc squared. For chemical reactions, there's a small change in energy. That was covered in thermochemistry and equilibrium. In nuclear reactions, there's a large change in energy. Again, that follows from the change in mass. And that completes the material of the lecture. Recapping the lecture. Isotopes are the same atom type with different number of neutrons. The band of stability comes out when the number of protons in a nuclei is plotted against the number of neutrons. Some combinations of protons and neutrons destabilize the nucleus. At low atomic number, the stability is where the number of protons is approximately equal to the number of neutrons. At high atomic number, stability favors an increase of neutrons over protons. We simplistically refer to neutrons as the glue that keeps protons from repelling each other in the nucleus. The nucleon are protons or neutrons and are bound together by strong nuclear forces. Separating nucleons releases energy, a lot of it. Radioactivity or radioactive decay refers to the particles and or energy emitted from nuclei of an unstable atom or isotope. Because radioactivity releases energy, it can damage living cells. Henri Becquerel and Marie and Pierre Curie were early pioneers of the research into radioactivity. Radiation is characterized as ionizing or non-ionizing. Non-ionizing radiation does not knock an electron off an atom. It is generally not dangerous. Ionizing radiation can knock an electron off an atom, and that leads to the formation of ions or free radicals. Radiation mainly comes from two sources. There's the man-made stuff like X-rays and nuclear power, and then there's background radiation that comes from sources like cosmic rays and radon gas. Radiation is accompanied by energy equals mc squared. There are three major types of radioactive decay. Alpha decay is a loss of an alpha particle from a parent nucleus. It is a helium nucleus, 2 protons, 2 neutrons, but no electrons. Beta decay is a loss of a high energy electron from a parent nucleus. A beta particle is an electron. Essentially, it has no mass and a charge of -1. Gamma ray emissions is the loss of a gamma ray from a parent nucleus. Gamma rays are electromagnetic radiation. They are light. They are high energy photons. Gamma rays have no mass or charge. In balancing nuclear equations, be sure that mass is conserved. The sum of the mass numbers before the reaction must equal the sum of the mass numbers after the reaction. Charge is also conserved. The sum of the nuclear charge before the reaction must equal the sum of the nuclear charge after the reaction. Include the charges of any particles emitted from the nuclei. And that concludes our lecture. What sets nuclear chemistry apart from other chemistry is that it produces a tremendous amount of energy.